With Jared Isaacman at the helm of NASA, humanity could soon set up a permanent moon base and then set its eyes towards Mars. But according to NASA, there's a big problem for humans traveling beyond the Earth's protective magnetic field: radiation. In this video, I'll explore NASA's ultra-cautious approach to radiation and ask whether it risks derailing our expansion throughout the solar system. But first, let's understand NASA's position. NASA's approach to radiation. NASA uses a model called LNT, or Linear No Threshold Model. This model is based on studying the effects of radiation from atomic bombs and nuclear plants and then extrapolating a straight line to lower doses. It's no surprise when using this model that NASA states that no level of radiation is safe. Following from this model comes the ALARA principle, which stands for as low as reasonable achievable. This principle colours everything NASA does and is particularly important and damaging to crewed missions to Mars, given the length of time astronauts will spend in deep space. To be fair to NASA, the whole US government has this attitude towards radiation. The LNT model on the ALARA principle originated from agencies well before NASA existed. NASA imposes a 600 millisieverts career limit on astronauts' exposure to radiation because, as NASA believes, no amount of radiation is safe. It's worth noting that ESA, the European Space Agency, has an astronaut limit of 1 sievert, or 1,000 millisieverts, substantially higher than NASA's limit. For comparison, on the surface of Earth, the typical exposure to radiation is around 2.4 millisieverts per year. NASA's strict limits on radiation exposure makes manned Mars trips difficult, as half of the career limit would be met just by travelling to and from Mars, without taking into account the amount of time on the surface, with a year on Mars exposing astronauts to an additional 245 millisieverts. Almost the entire NASA career limit of radiation exposure would happen in a single mission to Mars. For this reason, NASA prefers short trips to Mars to minimize radiation exposure. This directly conflicts with human expansion and settlement plans, which require extended times on other planets for exploration and to build out infrastructure needed for bases, resource extraction, and scientific discovery. NASA's approach to radiation will result in no meaningful progress on settlement plans. Heavier shielding inflates the mass of vehicles and habitats and the costs, while simultaneously reducing the science, exploration, and construction time available for settlement and expansion. Does NASA's view of radiation match reality? Water-Tsunami Analogy. At this point, I want to introduce an analogy to help explain NASA's approach. Radiation is invisible, so water can make it easier to understand NASA's models and thinking. Imagine modelling water's dangers based solely on tsunamis. Tsunamis, or giant waves, kill through overwhelming force. So under a linear no-threshold model, we would conclude that any amount of water, even a single raindrop, poses a drowning risk. Applying NASA's logic, we would further define an as low as reasonable achievable rule to water exposure. For instance, no exposure to swimming pools and avoiding going outside when raining, to limit exposure to water, which we have determined is unsafe at any level. That may sound absurd, and it is. But that's how NASA thinks about radiation. They extrapolate from extremely destructive events, such as dropping atomic bombs on people, to low amounts of radiation, which is what astronauts would experience traveling through deep space and living on other planets. NASA's strict LNT model completely ignores the human body's ability to repair damage from radiation, which is naturally occurring on Earth. For instance, potassium-40, which is radioactive, is found in bananas and lettuce. Radon and radium materials are found in rocks, and the gentle exposure to cosmic rays is non-stop. The human body quickly and efficiently repairs any damage caused by this type of exposure. There is no cumulative damage. The body fully and completely repairs all damage in most cases. NASA's extreme view of radiation, that it's dangerous at any level, will make it impossible to have long missions on Mars and push up the costs of any mission significantly. likely leading to delays and possible termination depending on the costs. Let's look at some real data on more realistic levels of radiation. Real-world data on chronic low-level radiation. Chronic low-level radiation is what astronauts will face when traveling outside the Earth's protective magnetic shield, so we'll look at the data to see how NASA model fits. A 2017 review article by Jeffrey A. Siegel and colleagues, linked in the video description, and published in the Journal of Nuclear Medicine, strongly criticizes the LNT model. The review argues that low-dose radiation, that is less than 100 millisieverts, lacks credible evidence and stems from, and I'm quoting here, flawed 70-year-old LNTH, which ignores protective biological responses like adaptive mechanisms, unquote. The authors state that far from low-dose radiation causing cancer, the opposite is true. It may help prevent cancers by upregulating the body's natural defenses against radiation. The review argues for abandoning the LNT model that NASA uses, emphasizing the substantial benefits of low-dose radiation used in medical scans. The report states that low-dose radiation of medical imaging has no documented pathway to harm. Let's move on to look at a place on Earth that has high levels of natural background radiation. In fact, the levels are higher than on the surface of Mars. Ramsar in Iran has naturally occurring radiation levels of 260 millisieverts per year, which is slightly higher than on Mars at 245 millisieverts per year. In a paper studying Ramsar, the authors stated there is no significant differences between people in the high background compared to people in normal background areas. In fact, the study found significantly reduced frequencies of chromosome aberrations to people living in high background areas. They conclude that the risk from high levels of natural background radiation found in Ramsar may be less than the predictions of the LNT model. In other words, real-life studies conflict with NASA's LNT model, and in the case of Ramsar, the radiation levels are actually higher than on the surface of Mars. Let's move on to how the human body responds to elevated levels of radiation and why these repair mechanisms ensure chronic low-level radiation is not harmful to humans, no matter how sustained it is. In other words, NASA's career limit for radiation exposure makes no sense and should be removed. Dose rate versus total amount of radiation received. As we have seen with the tsunami example, what makes water dangerous is not the amount of water, but the rate at which it flows. Large standing pools of water, or seas, are perfectly safe if reasonable precautions are taken. While a water cannon can lift people off their feet and slam them against the ground, it's the rate the water flows that does the harm, not the water itself. This is why it's astonishing, at least to me, that NASA makes no mention of dose rate when setting limits for radiation exposure. Under strict LNT, cancer risk depends solely on the cumulative total dose, irrespective of dose rate. NASA calculates radiation damage from high-risk acute exposures, specifically the bombing of Japanese cities, and then extrapolates the results to low dose rates. The only acknowledgement of dose rate, a critical factor, is a fudge factor NASA adds for low rate radiation. They don't call it that though. It's officially called DDREF, or Dose and Dose Rate Effectiveness Factor, which reduces the risk at the lower end by a factor of 2. This is NASA's only acknowledgement of the body's ability to repair radiation damage. ALARA, as low as reasonable achievable. NASA uses the ALARA principle in its radiation protection policies. This means that NASA doesn't consider any level of radiation safe, which conflicts with medical studies which find no danger at rates less than 100 millisieverts. ALARA means NASA needs to add heavier shielding, which increases mass and possibly flight times for vehicles, which in turn increases radiation exposure and makes vehicles and habitats more expensive. In NASA's zeal to protect astronauts from any and all kinds of radiation, no matter how low the exposure is, long-duration missions to Mars are put at risk. They either become too expensive and risk cancellation, or severely limited in capability with only short stays on the surface of Mars to avoid exceeding career limits on radiation exposure. Given NASA's determination to stick with this 70-year-old model, despite biological reality, is there any way that manned missions to Mars can be made more viable? Nuclear electric propulsion for manned missions to Mars. One technology that can help reduce radiation exposure is NEP, or nuclear electric propulsion. The first way it reduces radiation exposure is by cutting the transit time. Typical transit times using chemical propulsion are 6 to 9 months, resulting in 300 millisieverts of radiation for a round trip. Nuclear electric propulsion can cut transit times to 100 to 150 days, even less with highly efficient ion thrusters. This cuts radiation exposure in half, as well as reducing mass because fewer supplies are needed for the crew. The second way NEP helps is by supplying large amounts of electrical power on board to generate strong magnetic fields that can deflect galactic cosmic radiation. A nuclear electric propulsion vehicle likely will have hundreds of kilowatts or even megawatts of power available, enough to power superconducting coils that create a mini magnetic shield around the vehicle. NASA studies have confirmed that galactic cosmic rays can be reduced by 30 to 70% with active shielding. While NASA's career limit of 600 millisieverts is challenging, with a mission design using chemical thrusters, a mission using nuclear electric propulsion provides a viable path for manned missions to Mars while keeping NASA's stringent radiation limits in place. Risk versus reward. Traveling to Mars isn't risk-free, but as the new NASA administrator has said, NASA should be doing hard things and should take calculated risks. Are we getting the risk-reward ratio correct? Or is NASA right to be cautious in its approach to manned spaceflight? Take for instance this graphic, showing where all the bodies on Everest lie. Every year between 5 and 8 people die trying to climb this mountain. If people are willing to take the risk just to climb to the top of a mountain that has been conquered already, what about the risks of traveling to Mars and making life multiplanetary? Isn't that worth taking a risk for? Another example is smoking. The increased cancer risk of a mission to Mars, as calculated by NASA, is between 1.03 and 1.1 normal cancer rates. Smoking increases the cancer risk by between 15 and 30 times, massively exceeding the calculated risk of radiation exposure on a trip to Mars. But what about the other risks of a mission to Mars? Is radiation exposure the most important risk compared to the many other possible and far more direct ways of dying? A mission to Mars has potentially many fatal dangers along the way, from liftoff, transit, entry, descent, and landing. Success rates for uncrewed Mars landers are a coin toss at around 50 to 60%. Then there are the surface operations, which can result in spacesuit tears, contamination from toxic compounds in the Martian soil, to accidents leading to broken limbs. Add to that the dependence on life support systems, including the replenishment of air, water, and waste management. A long mission to Mars would need these systems to work reliably for years. The mission is one clogged filter away from disaster. Bone loss could be as high as 1 to 2% per month. Add 1/3 gravity on Mars, and any falls on the surface could cause broken bones. Healing would be delayed due to reduced gravity and lack of medical resources. Martian dust represents a severe hazard. With perchlorate present in Martian dust, hexavalent chromium is present in the soil and is a carcinogen linked to lung cancer. Any Martian dust inhaled or ingested would lead to acute poisoning, compounded by a compromised immune system due to the weak gravity. Add to that habitat leaks caused by micrometeorite impacts or seal failures that could cause depressurization to a near vacuum atmosphere. In short, traveling to Mars comes with a whole series of risks. It's not clear that radiation is the main challenge or should have an excessive effect on mission design and duration. Final thoughts. The long-term increased risk of cancer from a manned mission to Mars is perhaps 3 to 10%. If NASA thinks that's too much, perhaps they should cede the final frontier to other countries who are willing to take greater risks and reap the rewards. Do you think NASA's risk-averse approach to radiation is correct? Do you think it's worth the risk of sending astronauts on a long mission to Mars? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space news video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week, or in any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with previews of upcoming content. If you got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.